Here. Today we're going to be doing Unit 7, Note 6. So we're going to be talking about mutually inclusive and exclusive events. So first of all, let's just kind of take a look at an example problem here. So it says that a bag contains 8 red marbles, 12 blue marbles, 9 yellow marbles, and 11 green marbles. A marble is drawn at random, and we want to find the probability that the marble drawn is either blue or green. So we have 8 red, 12 blue, 9 yellow, and 11 green. So if you were to add 8 plus 12 plus 9 plus 11, you would get 32. So there's 32 marbles. Now, how many of them are blue? Well, 12. And then we want to figure out the probability of getting a green. Well, there's 32 total, and 11 of them are green. So when you add the top together, you get 23, and then we're going to divide it by 32. So 23 divided by 32 is 0.719. So that's the probability of doing a blue or a green. So let's go ahead and let's just jot some stuff down about mutually exclusive versus inclusive events. So mutually exclusive events are events that do not affect each other. So flipping a coin and rolling a dice, if you were to do those two things, their results aren't going to affect each other. That's what makes them independent of each other or exclusive. Okay, inclusive events are events that do affect each other. So for example, rolling a number less than 3 or less than 5 on a dice or a 1. Well, a number could be less than 5 and it could be 1. So when we do that, we actually have to subtract off the probability of them both happening because we don't want to count it twice. And it'll make more sense when we do an actual problem. So basically we would subtract off the probability in this example of getting a 1 because the 1 is counted here and here. Whereas if they're mutually exclusive, all we have to do is simply add the probabilities together. So let's just start by seeing if we can identify what's mutually exclusive and what's mutually inclusive. So drawing a heart or a diamond from a standard deck of cards. Can you be a heart and a diamond? Well, no, you can't. So that makes this mutually exclusive. Drawing an ace or a spade from a standard deck of cards. Could you be an ace and a spade? Yes, the card ace of spades. So that's inclusive. Rolling a 5 or a number greater than 3. Okay, can you be a 5 and a number greater than 3? Yeah, 5. So that's going to be an inclusive event because it can be both. Picking a red or a blue M&M out of a bag of M&Ms. Can you be a red and a blue M&M? No, you can't. So that's going to be mutually exclusive. So now we're going to go ahead and we're going to try some examples of these. So let's read through the first one. One teacher must be chosen to supervise a senior class fundraiser. There are 12 math teachers, 9 language arts teachers, 8 social studies teachers, and 10 science teachers. If a teacher is chosen at random, what is the probability that the teacher is either a language arts or a social studies teacher? Well, can you be both a language arts and a social studies teacher? For the sake of the problem, let's just say no. I know they're very rare cases, but we're not going to worry about those. So you can't be both. So since you're not both, what we're going to do is we have a mutually exclusive. So first thing I need to do is figure out how many teachers I have, which is 12 plus 9 plus 8 plus 10. And when you add all of those together, you get 39 total teachers. So now I need to see how many of those are going to be a language arts teacher. Well, I see that I have 9 language arts teachers. So there's 9 out of the 39. Then taking a look at the next one, I still have 39 teachers and I want to figure out how many of them are social studies teachers. Well, there's 8 social studies teachers. So now when I add these together, this is a really important thing to remember about adding fractions. When you add fractions, you're going to add the denominator, or numerator, sorry, and you're going to keep the denominator the same. So I added the numerator and I kept the denominator the same. So now to get my final answer, all I have to do is 17 divided by 39, which is 0.436. So that's my final answer for number 5. Let's now take a look at number 6. Suppose that out of 1,400 students, 550 take Spanish, 700 take biology, and 400 take both. So this 400 take both is a huge indicator because since you can take both, we automatically know that this could potentially, or this is, an inclusive event. So we need to look, how many students do we have? Well, we have 1,400 students. Okay, so I know that's my total. Well, how many of them take Spanish? 550. How many of them take biology? That's going to be 700. Then we know that there are some students that are taking Spanish and biology. So each of those students are being counted twice. So we need to subtract off the probability of it being both. Well, there's 400 students that are going to take both. So again, I'm going to keep my denominator the same. So I'm going to still have 1,400 on the bottom. Then I'm going to do 550 plus 700 minus 400. So when you do all of that math, you end up getting 850. So now all I have to do to get that probability is divide that out. 850 divided by 1,400, and I get 0.607. So that right here is your final answer for number 6. Now, let's take a look at number 7. There are 2,400 subscribers to an internet service provider. Of these, 1,200 own HP, 500 own Dell, and 100 own both. Okay, there's that both thing again. So since there is a both, then I know that this is an inclusive event. So we have 2,400 subscribers. So to start off with, I want to figure out how many of them own an HP. So there's 1,200 people that own an HP. Then I'm going to do the next one again, and I want to figure out how many own a Dell. And that's going to be 500. Okay, so now I need to subtract off the probability of being both, because there are some people that own an HP and a Dell, and they're being counted in for both of those. So I need to subtract off the probability that they own both, and that's going to be 100 out of the 2,400. So now I'm going to add, and subtract. So 1,200 plus 500 minus 100, that's going to give me 1,600. So I'm going to take that and I'm going to divide it by 2,400. So when you divide that out, you end up getting 0.667. So that's your final answer for number 7. And remember to always watch your rounding. I usually like students to have 3 decimal points. So you always want to look at the 4th decimal point and see if it's 5 or greater. So let's take a look at number 8. It says there are 4 algebra books, 3 literature books, and 2 biology books on a shelf. Doot, doot, doot. If a book is randomly selected, what is the probability of selecting a literature book or an algebra book? Can you be a literature book and an algebra book? I certainly hope not. I don't see many students reading the algebra book for fun, maybe except Mr. Pickens. Okay, so this is going to be mutually exclusive because you can't be both. So we need to count out the total. There's 4, 3, and 2. So we need to add all of those together. So 4 plus 3 plus 2 is going to give us 9 total books. Well, how many of those are literature books? Well, there's 3 literature books. Okay, then on the next one, how many of those are algebra books? Well, that's 4. And then we don't need to subtract off the probability of it being both because both doesn't exist. So 3 plus 4 is going to be 7. So we're adding the top, keeping the denominator the same. 7 divided by 9 is 0.778. So that right there is your answer for number 8. Now let's take a look at number 9. So for number 9, what we have is a game of bingo. The balls are numbered 1 through 75. The numbers that correspond to the columns on bingo card is shown in the table. So this tells us which numbers go where. A number selected at random. What is the probability that it is a multiple of 4, or is in the O column? So could there be multiples of 4 in the O column? Absolutely there could. Okay, so let's start out by writing out the multiples of 4. So we have 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48, 52, 56, 60, 64, 68, 72, and that is it. So those are all our multiples of 4. So now what I'm going to do is I'm going to write out the numbers that are in the O column. So I have 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, and 75. So I'm going to count how many of these multiples of 4 are going to be on the O column. So these last multiples of 4 are also in the O column. So that is our both. I'll be done in a couple minutes. Just give me 2 minutes. So let's go ahead and let's do that. So then we're going to count out how many we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we have 18 total multiples of 4 out of 75 numbers. In the O column, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there's 15 in the O column. And then we need to subtract off those 3 that are both. So 18 plus 15 minus 3 is going to give me 30, and that's going to be divided by 75. So there I get 0.4. So that's my final answer. That's the probability of getting a multiple of 4 or something in the O column. On this last problem here, let's take a look. A card is drawn from a standard deck of cards. What is the probability of drawing an ace or a face card? So face cards are Jack, King, and Queen. So can you be an ace and a face card? No, you can't. So these are mutually exclusive. So aces are one of our numbers of the cards. So there are 4 aces in a deck of 52. Well, how many face cards are there? There's 3 face cards per each suit, and then there's 4 suits. So 3 times 4 is 12. So 12 out of the 52 cards are face cards. So now we're going to go ahead and add across the top. 4 plus 12 is 16, and then we're dividing that by 52. 16 divided by 52 is 0.308. So that concludes your note video for today. Make sure you let me know if you have any questions. Thanks for listening.